We have a whole class of qualitative deltaS predictions. So you would either might be when you're comparing two systems that are very similar with one tweak, like the volume for a gas or the temperature or the complexity of the molecule. And then we also have questions where we're looking at particular reactions, whether they're physical or chemical. And then we need to decide just from our knowledge of entropy trends, if entropy will have a positive or negative change. So let's look at this first one. It's the sublimation of iodine, meaning we're going from solid iodine to gas phase iodine. And again, I encourage you to look through look through these questions through the lens of Boltzmann's law, where W is the number of microstates, which let's translate to the number of configurations. Right. And so if you have more configurations in the products, you're going to have a positive change in entropy. And so when we go from anything from the solid phase to the gas phase, so the entropy in the solid phase is always less than the entropy in the liquid phase is always less than the entropy in the gas phase. So this should see a big increase in entropy because now our iodine molecules are not sort of trapped in a small volume in positions where they can't translationally move or rotate. And so they get out into the gas phase and there's a huge bump in entropy. So this is a positive change. The reaction of hydride with water. So for these questions, again, it is so much about phase. So make sure you really pay close attention to like where our molecules are. We have some H minus, that's hydride, in water, and then it generates H2, which is a gas. So we're going to release two things that were in the condensed liquid phase or aqueous phase, and we're going to release H2 out into the gas phase. Again, that is going to be very significant in terms of how many microstates are available, even though water is the more molecular complex of any of these. Like it has, it looks like this and it has lots of, well, not lots, but like more vibrational modes than either H2 or OH, but it's in the liquid phase. And so, yes, that's more complex, but putting something into the gas phase is going to sort of trump this larger entropy, just because anything, again, in the gas phase is going to have a larger entropy. And here we have oxygen dissolving in water. It was in the gas phase, and now it's going into the aqueous phase. So here we had lots of freedom, lots of positional freedom and microstates or configurations because like there were just literally more places the oxygen could be. And then we put it into a condensed phase in liquid and water, and now we have a negative change in entropy.